All right, let's talk about a paradox that's probably hitting a lot of you AI engineers right where it hurts. This promise of giant context windows versus the reality that our models are still failing in weird ways. We're going to explore what I call the attention trap.
You've seen the headlines, right? 1 million token context window? It sounds amazing, like the final frontier. But if you've ever actually tried to stuff a huge document into a model and gotten a completely bizarre answer, you know there's more to the story. So what's the deal? What's really happening under the hood? Let's get into it.
So to really understand the problem, we need to build a simple intuition for what self-attention actually is. Don't worry, we're going to forget all the complex linear algebra for a minute, no Q, K, V matrices. Instead, just think of it like this. Attention is like a kind of gravity that pulls related ideas together.
At its heart, self-attention is really just a dynamic relevance lookup. As the model reads text, every single word, or token, is constantly looking around at every other token and making a little judgment call.
It's this simple three-step dance, really. First, a token looks at everything else in the window. Second, it asks this one basic question. How relevant are you to my meaning right now? And third, based on that answer, it assigns a connection score, a weight to that relationship.
And you know, this whole process is super intuitive. When the model sees the word refund, it immediately knows there's a huge gravitational pull to the phrase canceled flight. That gets a really high score. But the connection between refund and a filler word like the, almost zero gravity. That gets a super low score. That's it. That's attention at work.
Okay, so if attention is so smart, where does it all go wrong? This is where we hit the main problem, what I call the infinite context trap. It's this bizarre paradox where adding more information can actually make your model dumber.
In engineering circles, this has a name you might have heard of, the lost-in-the-middle phenomenon. It's that incredibly frustrating moment when you just know the answer is in the text you gave the model, but it just can't seem to find it.
And here's why it happens. As you keep dumping more and more text into that context window, you're not just adding information, you're adding noise. It's like trying to have a deep conversation in the middle of a loud party. All those smart attention scores get stretched thin. They get diluted across thousands of other, less important tokens. The model literally gets distracted, and the one crucial piece of information, the signal, is completely drowned out by all the static.
So theory is great, but let's see how this actually breaks in the real world. We're going to walk through a case study from a fictional company, let's call him SkyStream Airlines, to see just how expensive this attention trap can be.
So picture this. SkyStream builds a new AI customer service agent. And they do what seems logical. They feed it their entire massive knowledge base. I mean, more context is always better, right? Well, this new agent is about to get very distracted, and it's going to get very expensive. Okay, so here comes the user's question. It's simple, it's direct, but the most important token, the one little piece of information that should guide this entire search, is the word snow. That's the signal.
Now, buried deep inside that giant knowledge base, way down in paragraph 21, is the correct answer, the signal. It clearly says that delays caused by weather do not get a cash refund. Simple enough, right? But then, way later, down in paragraph 101, there's a distractor. It also talks about delays and refunds, but it's for a completely different reason, maintenance. This is the noise that's about to cause all the trouble.
And this right here is the critical failure. The user said snow. The model's one job was to connect that token to the weather policy. But because its attention is spread so thin across all this other noise, baggage policies, pet rules, whatever, it gets lost. It sees the words delayed and refund sitting right next to each other in that maintenance policy, and it latches onto that because it's a strong pattern, even though it's the wrong one. It completely ignores the snow constraint, and boom, the model hallucinates, and now it's promising a refund that it shouldn't.
So how do we fix this? We can't just keep throwing more data at the problem. We have to be smarter. The solution is all about how we engineer the context. We have to build what I call an attention spotlight.
Suddenly, the goal for us as engineers becomes crystal clear. It's not about providing all the information, it's about providing the right information. We have to take that messy, low signal-to-noise ratio and flip it into a high one.
And this is what success looks like. Instead of shoving the whole manual at the model, we can pre-process it or use a retrieval system to find only the most relevant parts. The user says snow, so we give the model just the context about weather delays. And now, look at that.
The attention mechanism has a bright, powerful, unmissable signal to lock onto. That high attention weight stops the model from getting distracted, and it prevents the hallucination.
I mean, the contrast really couldn't be clearer, can it? The failure mode is high noise, which leads to distracted attention, which leads to expensive hallucinations. Our engineering goal has to be to build a system that delivers a high signal, which creates focused attention, and that is what gets you accuracy. It's a fundamental shift in how we need to think.
So, this all leaves us with a really critical question we have to ask ourselves on our own projects. Are we treating our models like an all-knowing brain that we can just dump an entire library of information into and hope for the best? Or are we treating them like a highly specialized worker that needs us, the engineer, to hand them the right tools and the right focused context to do their job properly? Because how you answer that is going to determine whether you build a system that actually works or one that just creates really extensive mistakes.